My name is not Jürgen. So I think I don't know if any of you know, but Jürgen had a serious health issue this fall that prevents him from being here. And so, but I don't know if you'd like to just give an update, but I think we can all be encouraged that his health is recovering.
Yeah.
And, but you might, you know, I don't know how you approach, if you're a strict materialist, it doesn't matter, but if you have want to think about him and just give him some good energy, that'd be great. And then meanwhile, so my name is Goodman-Strauss, and I have really the honor to try to step in and just at least support his students in this. But I'd also like to, before we begin, could we just give our organizers a tremendous round of applause, because this has been amazing. I'm very grateful. And with that, I'll turn it over to someone who knows what he's doing.
Yeah, so my name is Michael. I'm a student of Jürgen, and I'm doing my Ph.D. with Tim together at the Technical University of Munich. And yeah, today Tim will start teaching you things. Tomorrow is my turn, and Wednesday is again his turn. Yeah, we'll see.
And I'll be here to support and just ask my comments from time to time.
Yeah, so hi, I'm Tim. I'm also not Jürgen and also not Uli Kortenkamp. But I am a PhD student of Jürgen. And as you can see, Michael and I, we are both a bit wet behind the ears. So we are very glad that Heim is supporting us. So the workshop will be about CindyJS. What is CindyJS? What can you do with it? Let me quickly show you this thing, which is not there, okay. I will just mirror the screen. Is it full format there? Ah, great. So this is a website which was created for some anniversary of TUM, and it features different applets which show mathematical topics of different faculties of our university. So it's not important what they are, but just see something of this. So this is a renderer of algebraic surfaces of some things. Then we have, like, this is a little simulation of diseases and epidemics and how different parameters like infection radius, infection rate, or vaccination rates, some things like this, influence the behavior of that, how you say it, of that dynamical system or that cellular automaton. And there's a swarm simulation. I don't know. It's not important what they are, but all of these are created using CindyJS. So this is to show you that we want to introduce you to some software which can be used to visualize a wide range of mathematical topics. Let's get back to the keynote. Oh, yeah. So, to introduce you to CindyJS, we have decided to spend the first day exploring Cinderella, which is the first software which laid the foundation for CindyJS and which we will see today, because it helps you to understand the way how CindyJS is built. And we hope learning Cinderella, you will get used to CindyJS way quicker than if we just introduced CindyJS as a standalone tool. So CindyJS will be tomorrow. On day 3, there will be CindyGL, which maybe connects a little bit to the other mini course, because we will also do graphics card stuff there. And then day 4, day 5, we will I think we will have plenty of things to talk about, and we will just fade everything off a bit. We talked about that, but we want to give some credit to Jürgen and Uli, who are the creators of Cinderella and the main creators of CindyJS. But you know us by now. So let's start. And I had that link up before we started today. And I would like you to install Cinderella. So you can get it via the link here. As I've said, we are not the creators of Cinderella, and Cinderella is actually old software, but we hope, I see many Macintoshes, so those should work. There we have plenty of experience that those will run Cinderella, but we also have experience with other machines. It should work. If not, please raise your hand. Michael and Chaim can run around and help you figuring things out.
Maybe raise your hand if you do have Cinderella right now. Let's see some more hands.
Is your own working for anybody? It's not for me.
Okay, that room is not working.
It is? It is for you? It is. Okay, so maybe it's just
Excuse me?
Is the version of Cinderella important for today?
No, the version is not. No, the version is not of any importance. So I will wait for 1 or 2 minutes because it would be really good if most of you have installed the software.
In a way, we're hoping that, see, like you could give a very fast lecture over all the features, but we're hoping that we give a very slow presentation where you're more like, wait, how does this button work?
Yeah.
We can come around and help you.
Exactly. So generally, the idea is that not only today, but also the other days, we do some stuff here in front of you, but we don't do it in a simple presentation format, show and listen. But our goal would be that at the end of every 60 minutes, you have something running on your own laptops. Let's see how that goes.
So do let us know. We'll come around and help
Yeah.
you.
So who is in the installation process and who's okay? I think Martin is a great benchmark.
no.
It's a lot of pressure.
Yeah.
There is a problem with the everyone Wi-Fi network.
Okay. But is the visitor Wi-Fi working here? Is it available here? Okay.
So let's cut it 9:50, so we have 10 minutes.
Yeah.
So mine says starting installing.
Starting installing, great. Does it give an estimate?
It gives me a next button.
Okay. So that's one of the advantages of CindyJS. We will see tomorrow. There's no need for installation. We just built browser-based tools starting tomorrow, and then we will have less problems sharing the things with you. Also, my voice is not at its peak state right now, so please excuse if I'm coughing or mumbling. The agenda slide, yeah, sure. Okay, Martin, are you finished?
I'm trying to start it now.
Okay,
It says math in motion. Is that good?
I think so. Great.
I hope so. I see a window.
Yeah. So what all of you should be seeing is something like that. And admittedly, as I said, it's old software. It doesn't look fresh and modern, but it can do a lot of things. To get you quickly used to the interface, the buttons look overwhelming, but they have structure, of course. So the bottom line is just to adapt your view, the gray window you see. The first row contains file handling, undo, redo, and the selection tools for geometric elements. And everything else is for geometric constructions. And if you click or hover over a button, you will always see a description text of what that button does and how it should be used. So it's kind of a quick helper menu built into the software. But it is a bit confusing at first to use the software. You can unclutter your view a bit if you do this thing, configuration, choose toolbars and set it to default. This will make some buttons disappear, which we won't need. Okay. And starting now, we will work with Cinderella. I don't know if it's maybe not helpful to put it full screen, as some things are moved around. So let's do it like that. One tool which we will need a lot is, it's very simple, to draw lines and to draw segments. So besides points, the most simple stuff you will find in the software. And a Cinderella is built to be user-friendly-ish. So there are always several kinds of how to use the buttons. But most of the time it will be something like that for the segment. You want to draw segments, so you click at one point, drag to the point you want to connect it to, and then you let go. So very simple. Very simply, we can build a triangle. Okay, nothing too exciting. One interesting geometric thing belonging to a triangle is the so-called Euler line. And we will build it now. And it connects different special points connected to a generic triangle. So, first of all, we want to draw the heights of the triangle. And to do this, we choose that tool, Draw Perpendicular Line. And as I said, there are different methods you can use. So one thing is you can go back to move. You can shift-click a point and a line. Then you can click this. And then you have selected a point and a line. And it will draw the perpendicular to the line through the given point.
Raise your hand at any moment if you need.
Yes, exactly. Michael and Chaim are glad to help. Alternatively, you could select a line, having chosen the perpendicularity tool, click in it, and then you get an orthogonal line which is movable, and then you can just click the point here to have it fixed to that point. To have the second height, and then we draw the third height. And as you see, all of these three lines meet in a common point of intersection, and this is no coincidence. So if you start moving the vertices of your triangle, that property still remains true. And actually, by doing the dragging stuff, it's kind of a probabilistic proof already for the property that these heights meet in a common point. But of course, you can prove that using elementary geometry. To make it a bit more visually, a bit more overviewable, we can select the lines and press Command-I to open an information window, Command-I, as you would think, and then we can choose. Okay. In case there's no Command-I, there's also, so everything can also be reached via the top bar here, and where do we have it? Under Edit, last thing, information window, opens that thing here. And this is some dialog window where you can edit a lot of properties concerning the whole construction, but also concerning the list of selected elements. So in this case, we have selected the 3 lines, and let's just give them another color, a different color, to make them stand apart. So, great. Let's build other lines. Namely, we will need the midpoints between the sides of the triangles. For that, you use the midpoint tool. And again, one opportunity would be to select the 2 points you want to determine the midpoint of and click the midpoint button. But alternatively and more intuitively, you can also start by clicking a button, dragging the free new point to the one you want it connected to, and there you have it. So now we have the 3 midpoints. And now we can also draw the perpendicular bisectors. So not the heights, but again, perpendicular lines going through the midpoints of the segments. Nice. And also these lines are intersecting in a common point. And again, this seems to be no coincidence, but remains true for basically random positions of our points. And again, let's give them different colors, just for fun. So let's make them green. You can go to the move mode, which is, generally speaking, the move mode is extremely important because I use it to select things, and you want to move your stuff around, and then you can just make a window, drag a window. What you can also do is to hold Shift and click the elements you want to select.
Could you just show us doing like 2 things instead of all of them?
I don't understand. What's the question?
So shift click on another dots and then you can do both of them?
I don't know if that's possible.
You might be repeating the question because of what's
Thank you. The question was if it is possible to select multiple points and move them at the same time. And I don't know, but the answer is yes, that is possible. Nice. But I think it's only possible in such a case where you have selected 2 freely movable points, of course. I didn't know that. So we also might be able to find, we might be able to learn some things because we're not the creators of the software. But we know a bit about it. And the last thing is, going back to the line tool, we can connect the midpoints to the opposite corners. In German, it's the Seitenhalbierende. In English, I'm not sure. But it has a name. And also these intersect in a common point. Let's make them purple. Okay, now we have these points. And now one sees, maybe the points G, H, and K, they seem to lie on a common line. So let's check by drawing the connection line of G and H. So, and this is crucial now. When I do this, I define the line to be the join of the points G and H. And now I see, even if I move stuff, it still seems to go through point K. Let's color this stuff differently to make it clearer. Let's make it all black. And let's make the line a bit thicker. But it seems to be true. And one thing which I just mentioned, that Cinderella can be used as a probabilistic prover, is actually built into the software. So if we look at that line, we can go to the little I in the information text. Wait, where is it? Okay. No, I would have expected Cinderella to give us a probabilistic proof that K is indeed always on that line, but somehow it's not working, so never mind.
It works on my machine.
It works on, on Michael's machine.
But there's something I'd like to just emphasize, that as a group of mathematicians, I think you all get this, but with teaching dynamic geometry in general, it's a big deal to explain the dependence. So that line depends on G and H, and it's just coincidentally passing through K. And
Yeah, thank you.
Middle schoolers, you'll know how big of a deal. So my point is that the line, to a group of mathematicians, it's obvious, but if you're teaching middle schoolers, believe me, this is an issue. So line G and H, the line depends on G and H and not, it just coincidentally passes through K. And so, of course, as you use dynamic geometry, these dependencies are very, very important to the whole business. Again, I don't think that's an issue for this crowd, but it's very much an issue with this kind of software.
Would you say it's a coincidence, or would you say it's a theorem?
Oh, well, no, it's literally coincident.
Oh.
But whether it's a coincidence or not is a theorem.
Okay, I hope you're a bit more familiar to the software now, and let's start to do some more serious things, which is to understand the underlying geometry of Cinderella, but then also of CindyJS. Because Cinderella and CindyJS, they are not set up as you might expect in usual Euclidean coordinates, but instead they work using homogeneous coordinates and projective geometry. Who of you has not worked with projective geometry before? Great. Who of you feels really familiar with projective geometry? Okay, but I think it was hard for me to read you as an audience, so I've prepared a short reminder. Maybe it helps, but if you say, that was too fast, please let Michael and me know, and we very happily provide you with very good introductory material, because I think it's very, very, very good to know some projective geometry as a visualizer.
Advertise Jürgen's book.
Yeah, we could just advertise Jürgen's book, but at the same time, it's huge. So, the idea of projective geometry is to use a projection. That is, to use spatial geometry and a projection in that geometry to express planar geometry. What we do is we take a field K, Usually that will be the reals or the complex numbers. And we identify points as one-dimensional subspaces of k to the 3. So like in that picture, I've drawn that line labeled as P, which is a one-dimensional subspace of R3. And what we already see, what the idea is to take an intersection plane and only consider the point of intersection in the plane. And the one-dimensional subspace will represent that point. Similarly, lines are the two-dimensional subspaces. So the line in that projection plane is in R3 a two-dimensional subspace, namely the plane that intersects the drawing plane in the given line. But we express it also by a one-dimensional subspace, namely its orthogonal normal subspace. So this is the thing labeled L. And if we do so, we get something called homogeneous coordinates. What is about that we just pick a representative of the one-dimensional subspace, because everything which is non-zero spans the whole subspace. So we identify all non-zero scalar multiples to express the subspaces. And doing so, we get something called far points, which I won't explain now, but I will show you in Cinderella. And the nice thing is that the incidence relation, that the point P is incident to line L, becomes a simple scalar product. P is incident to L if and only if the two subspaces are orthogonal, which is nothing else than that their scalar product vanishes. What is also nice is if you are given two general points or two general lines, other than in just plain R2 Euclidean geometry, it is really, really simple to determine joins of 2 points and meets of 2 lines, because it's expressible as a cross product using homogeneous coordinates. But points and lines are not the main motivation. So the nice algebra, which we already see here, carries over to the theory of two-dimensional curves, the conics, but also to higher degree objects. So quick excursus. Call us if you want to know more. To show you the projective nature of Cinderella, let's open a new window. I've done it using Command N, but you can do File New. And what I want to show you is at the bottom here, you can draw a rectangular grid. And you can also have activate the magnet here, which will make points stick to the lattice points. So you will see them. You will see if you drag it around, and then if it is close enough to a lattice point, it will snap. So I've told you that there are things called far points in projective geometry, and what they do is they make that Euclidean concept of parallelity explicit. So because what happens in projective geometry is that if two lines are parallel, they have an intersection point, which is a far point. And we exemplify this by drawing two lines, one like that and one like that. We take the intersection point, and now we join a different point with that one. So, and what we use the lattice for is to ensure that we can really drag the lines into exactly parallel positions, because if we move the point D to that position of parallelity, this point E will move to the corresponding far point of the parallel lines, like that. And then what one would expect and what really happens is that this line becomes parallel to the other two.
Just to sort of reflect on that, I mean, just if that, I mean, obviously, if he didn't if in, like say Geometry Sketchpad or GeoGebra, what would happen is that E would just simply not exist and that lower line would vanish.
Yeah, that's generally a good comment. So there is, so I know about Cabri, Geometry Sketchpad, and GeoGebra, and as far as I know, all of these are not based on projective geometry. I know GeoGebra has a workaround for that specific kind of situation. So this line will still exist, but you can you can build examples involving more far points where it just breaks down. One thing is that Cinderella doesn't only work using projective geometry over the real numbers. In fact, it uses projective geometry over the complex numbers. So let's erase everything. I select everything here, and then I click the eraser. What happens is, this is a general example, we can take two circles and join their intersection points. Okay, and then you get a line, nice.
How does it, question, how
Yeah.
does it represent the intersection points, internally?
Internally, it calculates all 4 complex intersection points and gives them an order to identify them under motion.
And where does it keep the other 2?
They are not visible, but internally they're there, and that is exactly the point. So if I drag them apart, as two-dimensional curves, they always have, by Bézout, 4 points of intersection, but in this case they vanish. But now the gist of Cinderella is that while you construct in RP2, you really do your calculations in CP2.
Wait, sorry, maybe I'll ask my question again.
Yeah.
How does it represent the points of intersection internally? Are they floats? Are they
Oh, they're complex floating numbers
complex floats?
using homogeneous coordinates in CP2.
Okay, thank you.
But then they also have a structure on them too, because in dynamic geometry, telling points apart is always a challenge. And then now the nice thing is that the 2 points of intersection, which we have defined earlier, now become complex conjugate points by moving the circles apart. And if you now take the join between those complex conjugates, you get a real line. And that's why the program is still able to draw the line. Because natively, and this is also the case for CindyJS, if you have geometric objects, all the calculations are done using CP2 coordinates. So you can, in particular, you can work with complex numbers in CindyJS without defining your own complex data structure or anything like that, which is a cool thing. And also that is, as far as I know, a unique feature of dynamic geometry programs.
Could you show us how to break it? So if some coordinate gets really big, then something bad should happen.
There are.
Can you repeat?
Thank you. So the question was how you can break that thing. And so what I know is there are examples where, because the difficulty is you have these 2 points of intersection, and the real difficulty is when you move other points, it is a challenge particularly in situations like these, where those 2 points are extremely close to each other. The challenge is to tell them apart. And that's why I don't have one by heart, but there are examples where you have like wild singularities, and if you pull points through those singularities, it just computationally breaks down, and then points get messed up.
What about making them concentric, or making them concentric with the same radius?
So I don't know any simple example where it breaks down. One thing I wanted to show you anyways is the following thing. Because in the world of dynamic geometry programs, there are the notions of so-called continuous and conservative models. And to exemplify what I mean, I draw a line. And then I put 2 circles with the same radius on that line, which maybe goes in the direction what you have said. And then I take this point of intersection. Now, if I move this, what I would expect is that the point E stays on top if I pull through. And this is exactly what happens so there's this one singular situation where the circles coincide, and of course you cannot tell the point E at that point of time. But otherwise, this behaves just as you would expect. And as far as I know, there's no other program which has this behavior. And this is what we call continuous behavior of a dynamic geometry program.
Let me just back up and say that in Geometer Sketchpad and GeoGebra, the behavior would have been that E would have flipped to the other intersection, because if the order of it's somehow calculating it by which circle's on the left and blah blah blah. I don't really know. So just again, this program is working so well that you have to understand what the other programs are not doing. Sorry about that.
No, let's quickly show it.
Oh, you have it. Great.
So one thing, it looks like it snaps, but it's not snapping. So we have to tweak this.
That's
Okay.
evil, so it looks like it's snapping. Is there
Yeah, it looks like it is, but
there's
it's
a
not.
mode to make it snap to grid?
I don't know.
Okay.
So I haven't found it. So let's take this point of intersection. And now if you move it, it will always jump.
And the same in Geometer Sketchpad.
Same in Geometry Sketchpad. Really?
Well, so much for that.
Really?
Like I moved the point over to the side and my intersection point flipped to the bottom.
That is surprising. And Jürgen would be horrified to see that. Because that is one of the main selling points. Because
Because you're not doing the same. You're not doing the same. Yeah, that's a different matter. He's doing a different experiment.
he's doing it. You have like you probably had like similar but slightly different radii, right?
No, he's going to 0. The radius is going to 0.
The radius goes to 0. I see.
So it passes through a singularity.
Yeah, singularities are bad.
No, but it's still continuous.
It's still continuous?
Yeah.
Okay,
Everything goes
perfect.
to 0.
Perfect. And this is,
About the behavior of this?
yep,
If I move my circles so they go apart and then bring them together again, E seems to swap from the top to the bottom.
exactly.
The rationale behind that?
Yeah, that is the next point I wanted to talk about. It's not simply that I want to call out GeoGebra for having a bad behavior. No. It's just a different design choice. Because what GeoGebra does is, if you move your things around, if you come back to the position you have started with, like this point C and D, E will always be at the same place. You can do whatever you want. If the centers C and D are there, E will always be here. This behavior is called conservative. In Cinderella, however, this is exactly what you have noticed. If you do this, oh wow, point E comes back at the other side. And just this is a resemblance of a monoptromy effect happening in CP2. Because you change, you can imagine that you change the sheet of your configuration space.
You say it resembles monotone or it is monotone?
It is. Yeah, it is. Great. And this, to model stuff like that, it's crucial to do your calculations in CP2.
Sorry, can you show this one more time?
Yeah. What happens if you drag the circles apart and then reconnect them? E jumps between the two sides, and that is E changes the sheet of the configuration space of two circles having two real intersection points. It's like this is a singular position, and by moving around the singular position, E goes back and forth, while in GeoGebra, once you have the positions of C and D, you can always tell where E is. In Cinderella, once you know the positions where C and D are, it may be that there are different solutions where your dependent point might lie. Great.
So not only continuous, but also differential.
No, but continuous, really. Oh, why not? But also, yeah, oh, sure, yeah. Yeah, but also differentiable, right? Okay, what have we left? Great. So maybe we can talk a bit about the project sheet of today. We have, so as Martin said, what we always did is we provided different tasks or project tasks. Some of us who are new to the field, like Michael and I am, will to do all the things which are proposed there, it would take days. But for the visualization veterans in the audience, many things are probably extremely boring, and so we tried to include some examples which are open-ended and what might interest you. In any case, please, if you have an idea, work on it and ask us if we can help. So there are three project proposals on the sheet of today. First, we encourage you to do some classical geometric constructions. If you have been educated like Michael and me, you will know these things. I think for Heim it's basic knowledge.
No, it's already dead when I got to school.
It was already dead, okay. So you're encouraged to use all those construction tools of Cinderella. Then there's a topic about straight edge and compass constructions in hyperbolic geometry. Many of you will already have seen this. And Chaim had the idea that maybe if we find an engaged group, we could also do that outside using some chalk and a string on the ground. So we are happy to do that with you. And excuse me?
Do you have the string?
We will find some string, yeah. But it wasn't a spontaneous idea, so we don't know if there is, but we will find. And then there's another thing about locus curves. And I want to show you what they are now.
I should also say that we will be around at some points this afternoon for the workshops. We want to talk about these things.
So exactly, what Kaims just said is we will be here in the afternoons to talk with you.
I have a question. Can you change the dependencies?
The question is if you can change the dependencies.
So if there are 3 points on a line, there's no way to drag the line, move the line by dragging any of the 3 points. You can only drag 2. You can only move the line by moving 2.
It's just conceptually the way it's like logical dependency.
Yeah.
So the example is if you have a line like this, you can move that point C on the line, but you cannot move the line by moving C. And if there is the possibility to redefine that. This is difficult, and there is a tool that does a similar thing. I avoid it because if you have more complicated constructions, it's tricky to keep everything in mind. But there is that wrench. And what it says, it detaches and reattaches points. But I think this is not what it cannot, yeah. So what it can do, if you select C, you can deattach it from the line or reattach it, But what you cannot do is to make this 3 points A and B leave the line. So no. To your strict question, the answer is no, but there is the possibility to do kinds like things like that, to later on change incidences in your constructions, which you haven't done earlier.
We should show them.
Yeah, but before we do that, I wanted to show you locus curves. And let me give you a simple one, which is, let's take, we don't need the grid. Let's take a circle. I've used this circle here. There are different kinds of circles in the program. There would be also this. The difference is that in this case, the radius is given implicitly by another point which lies on the circle. And in this case, you have a radius in the definition of the circle, which is nice because you can just have the circle as it is. So let's delete that. Oh, and at the same time, I hope I was not constructing too narrowly for you. It looks fine on my window, but I hope it's big enough that you can see everything. So, locus curves trace out the path of elements under the one-dimensional motion of other elements. So, what does that mean? Let's take a point that is lying on the circle, so it has one dimension to move. And using locus curves, we can show the behavior of dependent points of that. So, in most simple thing I can think of, take another point C with fixed position, take this midpoint D, and then we can use that locus tool here, the little figure 8. And then it says, choose the moving element, point or line first. So our mover is point B. In this case, the road of the element is already determined because it can only move along the circle. And now we want to trace what point D does, and okay, by moving B, D just walks on a scaled version of the circle B is walking on. And this, of course, depends on the position of all these elements. So that is simple. Let's build something more complicated. I will delete everything and build it ground up. So let's take another circle. So we start off in a similar fashion and put a point on the circle. Then we draw a tangent at that point. So what we do is we draw a radius, and then we take the perpendicularity tool and put it here. So we have a tangent. Alternatively, if you know about projective geometry, there is at some place I think by cleaning up the buttons, I've removed the button I wanted to show you. But never mind, you can reach everything via the top menu. And then you have modes, point, points line, polar of point. And if you know about projective geometry, the polar of a point with respect to a conic for a point on the conic is the tangent at that point. And you can do generalized polarity operations in both directions using Cinderella, but I've just built it manually here. Okay, and then take another fixed point C, and then we take the orthogonal to the tangent through C. So, does anyone know the construction? What is the movement behavior? What is the curve D is following? it looks like an ellipse. Does it? Not really. So let's draw it. Looks like that. So it's I've forgotten the English name. Is also limaçon. Yeah, I think it's a limaçon, but it's a cardioid. But I don't know about these curves, so you know more than I do. I think that's right. That's a cardioid. If C lies on the circle, but this is kind of a generalized cardioid. Great. Okay, and now that you know how to build locus curves, you're also set up for the third task, and we will have to discuss how we share the things with you.
We will. There will be a link
There will be a link
to like some online folder
to an online folder
in the Discord channel,
in the Discord channel.
and there will be the stuff.
And there will be the stuff. Unfortunately, I also had this issue yesterday. My overleaf is not working. So I try to reopen Safari. Ah. So. So, this is what we have thought of today, but as we have said, we might have new ideas while working with you guys. So there might be changes to these sheets. But as I've said, so project 1 concerns classical geometric constructions. We included little images to help you use the software, because even for me, it's oftentimes confusing how to use it. Then we want you to use Cinderella to make compass and straight edge constructions in the Poincaré disk. And what Keim did is that he prepared something beautiful, and we want to encourage you to build something similar, if you would like, which is the 6-4 tiling. Would you like to say something about it?
I'd say very, very briefly that this looks incredibly complex, but it isn't really. And that in the folder, there's a number of leads you through step by step how to do this compass and straight edge construction. And in fact, for any this particular one, for any P4-2 tiling, where P is like greater than whatever it needs to be, and it's great. This is a wonderful piece of geometry. M.C. Escher discovered this for himself, based on a single drawing of the hyperbolic plane that was sent to him by Coxeter, which is fantastic. I have to say, M.C. Escher was a mathematician, despite what he had to say about it.
Would you like to say something about the perspectivity thing?
Yes, I would. So there's also another, that's in the folder as well, another construction which I think all of us should know, and I'd love to show you how this works. So this is something that we have no time, but if you print this piece of paper out, you can make a little demonstration of actually on a piece of paper how to draw. So like if you only took an art class, you might have learned about 1 point or 2 point or 3 point perspective. That's garbage really, because I mean, I don't think that really actually people that use perspective truly would ever, I don't know. But you have arbitrary point line perspective, and so how do you take an arbitrary line from an arbitrary eye point and draw it in proper perspective? And it's a very simple technique, which of course goes back hundreds of years. And this is a little demonstration. So you can actually draw, the original project here was to draw an icosahedron in perspective, and I'd be happy to show any of you how this works. But the starting point is you just simply print this out on a piece of paper and fold it like this, and you have a whole demonstration of how it works.
So maybe we are able to print something out in the library, but...
Yeah, but either way, it's easy to understand how. It's a fantastic thing, and I think especially since we're illustrating mathematics, and we, you know, let's look back 600 years and think about, I mean, this is really worth knowing, so.
Yeah, I don't need it. Great. I mean, yeah, let's wrap up then, right?
I have one more thing to say about this construction. So if you look at, for example, Avesta Mathematica, which is a journal, or any number of other sources, there's a particular tiling of the 732 tessellation, which goes back to Klein's paper in 1878, and it was reproduced over and over again for now, 150 years now. And it's the same damn image. You can tell because it's the same cross marks in the same place. And so it was made, yes, that's right. And it was, this looks like a recopy, actually.
Yeah,
because those
but
cross
it's
marks
also-
are going in a different way.
It's
But,
also
but how was that made? This is the technique. So there really is a whole history prior to the use of computers for doing these kinds of things. And that's sort of a sideshow. But I think it's worth knowing. I mean, in this conference, I can't push that hard enough. I would love to have some people leaving here knowing something about this.
Great. So thank you. We're out, and see you in the afternoon.